Okay, in naive Bayes, actually what we've learned previously pretty much is about naive Bayes, where we focus on maybe changing this probability of x given y equal to class C. And yes, the core idea of this algorithm is that it depends on our assumption of our input feature distribution that is given the class, right? So that's like the only thing that is matters in this classifier. Like you change that term. But is there anything else that we have to concern about when we use naive Bayes? Actually, my previous example, when I wrote this, that FC, when we wrote like f of x equal to Gaussian like that, simply there was implication behind that is that it's like, in this example, I was consider x as a scalar value. So it's like my input feature is just one dimension because it's scalar. But what if there are more than a scalar value? What if we are considering like a vector of input feature? Just like in this example where you have x in 2 dimension. X could have 3 dimension or 4 dimension, doesn't matter, because all you're using is like the correlation between probability of x given y. But if x has high dimension, that means that there are some complication as to how you would compute prob of x given y. Isn't that right? Like if x is a scalar, then it's a scalar Gaussian random variable. But if x is a vector, then that's multivariate. It's like it will start to have 2 means, or maybe the covariance may not look like, like identity matrix. Maybe there are some negative covariance, there are positive covariance along the way. So that is something that you will have to figure out if x has higher dimension. But the thing is, in naive Bayes, there are additional assumptions that people usually make. That is, if xj that we used previously is n-dimensional features, usually we'll make assumption that they are conditionally independent. That is, if we have probability of x given y written like that, and yes, if x has high dimension, you can like a joint probability between each xi, like for each I being like the coefficient in n dimension. Or on the other words, your xj is now being in Rn, right? And you can actually write it as a vector x1, x2 up until xn, just like that. But it's of the j sample. What we usually do is that instead of computing the joint distribution like exactly like this, in most cases we will further make assumption that they are conditionally independent. That means given yj may be equal to class C or class whatever class it is, you assume that each and every x given y here are independent. That means that you don't need to write, okay, maybe I'll just put this way. If you don't assume the independency, usually we will end up with x1 up until xn, and this is like of the j sample. It's pretty long vector, and if you have to find the probability of this joint distribution, it could be a big thing to do. So maybe you better do something like, if you assumed independency, you probably end up with xi of j sample given yj. So it's just like that. So yeah, so instead of having to consider the multivariate version, you probably want to consider like a small version of it. That is individually, how is the probability of xi given yj. Yeah. So that is the conditional independent assumption. But this assumption is usually being violated, or it's not necessarily true, because it is possible that you will have like a feature vector that its coefficients are somewhat correlated to each other. Just like our previous example when we talk about like the credit card default, like the fact of being students initially kind of give you like a chance that your credit card will be default. But then when you have other features that are related to it, like the credit card balance, well, usually students have higher balance than most people because we have to pay tuition fee. But when we consider that there are some kind of relationship between being student and the card balance, then that correlation are not independent. They are related to one another. They impact one another. Therefore, this assumption wouldn't be true. But people normally use it otherwise because it's easier to compute. So this assumption will normally be, like violated. But yes, it's kind of simplify your calculation. But yep.
When you use this assumption, you are taking the average or something like that.
Sorry?
Are you using the average, or like you have different x from xi to xj?
Yeah.
With respect to level y.
Yes.
You're taking the average of it, and you decompose the.
Not sure about what you mean by average.
Like for example, you take for your xj.
Yep.
1 xj1 over yj. Then you take xj2 over yj, xj3 up to xjn. Are you taking the average of the values?
I think it depends on the assumption of what xj is. I think I'm not sure about your question. Sorry, maybe can you write down what that means? Okay, I'll pause.